Dear learners, I will discuss on simple harmonic motion. Simple harmonic motion. If a body is acted on by a force minus kx, the force is of this type minus kx, that is the force is proportional to the displacement and it is directed opposite to the displacement. Then it achieves a periodic motion in a straight line. This motion is called a simple harmonic motion, and the body associated with this motion is called a simple harmonic oscillator. Let us consider a toy car on a horizontal frictionless table with a vertical wall W. One end of a spring is attached to the wall W and the other is attached to the toy car as shown in figure. The spring is in a normal state. The center of mass of the car is at a point O. O is written down here. The resultant force on the car in this state is 0. So O is called the point of equilibrium. If we pull the car horizontally with a force Fe, the car moves to a point P and stands there. Fe is the external force. OP is the displacement x of the car. X is also the extension of the spring. Fe, the external force Fe, is proportional to x according to Hooke's law. That is Ap equal to Kx. K is called the spring constant. K equal to Fe divided by x. From here we can define the spring constant K. It is the amount of force needed for unit extension of a spring. That is, the force needed for unit extension of a spring is called the spring constant. K is large for a hard spring and it is small for a soft spring. A restoring force F is created within the spring and it acts on the car towards the equilibrium point O. The external force F and the restoring force F are equal and opposite. Therefore, we can write the restoring force F equal to minus F external, that is minus Kx. The restoring force F equal to minus Kx. If the car is pulled to a distance A from here to there, and if the external force is withdrawn, then the car executes a simple harmonic motion. The restoring force at a displacement x is minus Kx. This force produces an acceleration of the toy car. According to Newton's law of motion, mass into acceleration equal to the restoring force minus kx. M is the mass of the car. The acceleration of the car A equal to dv by dt, rate of change of velocity with time, equal to d by dt dx by dt. V equal to dx by dt, that is ds square x by dt square. Then we can write m ds square x by dt square equal to minus kx, or ds square x by dt square equal to minus k by mx. K by m is a constant, and this can be replaced by omega square. Omega square equal to k by m. Then we have ds square x by dt square equal to minus omega square x. It is the differential equation of a simple harmonic motion. We will solve it. That is, we will find x as a function of time t. We multiply the equation by 2 dx by dt. Then we may write 2 dx by dt ds square x by dt square equal to minus omega square 2x dx by dt. Dx by dt equal to v. Therefore, dv by dt equal to d by dt dx by dt, that is ds square x by dt square. So we can write here 2v dv by dt equal to minus omega square 2x dx by dt. d by dz y square equal to d by dy y square dy by dz, that is twice y dy by dz. Therefore, twice y dy by dz equal to d by dz of y square. So we can write twice dx by dt twice v dv by dt equal to d by dt of v square and minus omega square d by dt of x square. Integrating this, we have v square equal to minus omega square x square plus a constant of integration c. This constant can be found out from initial condition. The condition is that when x equal to a, v equal to 0. Therefore, we get the value of c 0 equal to minus omega square a square x equal to a plus c, that is c equal to omega square a square. Therefore, v square equal to minus omega square x square plus omega square a square. Omega square is common, a square minus x square, from which v equal to, we may write omega root over of a square minus x square. Putting the value of v dx by dt equal to omega root over of a square minus x square. Now we separate the variables dx by root over of a square minus x square equal to omega dt. After integration, we get sine inverse x by a equal to omega t plus constant of integration c dash, c prime. Again, the constant of integration c prime can be calculated from an initial condition. Here, initial condition is this: when time is 0, the car is at somewhere there, it is at a distance L, that is, when t is 0, then x equal to L. When t is 0, then x equal to L. Then we can put this value in this equation, sine inverse L by A equal to 0 plus c prime, that is c prime equal to sine inverse L by A, and this is a constant. We may write delta. C prime equal to sine inverse L by A, this is delta. Then the equation becomes sine inverse x by A equal to omega t plus delta. Therefore, x by A equal to sine omega t plus delta, or x equal to A sine omega t plus delta. This is the solution of the differential equation of simple harmonic motion, and it is the displacement at any instant t. It represents the displacement of the car at any instant t.